So folks, today I have come with this problem of 2023. You can see here 2023, February, March, paper 4-2, and the question number is 8. Yeah, question number is 8. So this question says that plutonium 238 94 Pu 238 is unstable and undergoes alpha decay. Alpha decay. So this is stressed here, alpha decay. And I complete the equation to show the decay of plutonium 238. So it goes alpha decay. So for alpha decay, the specifications are it will be 2 and it will be 4. So 2 is the charge number and 4 is the nuclear number. So it is 2, 4 alpha. And then for uranium, it should be equal to, so out of 94, 2 is gone. So it should be 92. And out of 238, 4 is gone, so it should be 238 minus 4 will be 234. So this should be the numbers there. Now next is a power source in a space probe contains 0.874 kg of plutonium, it says. So this is the initial mass of plutonium. Each nucleus of plutonium that decays emits 5.59 MeV of energy. This is the energy. The half-life of plutonium is 87.7 years. So this thing is equal to T 0.5. I often prefer to write T 0.5. Some people write T 1/2, but I prefer to write T 0.5. So now we have to calculate the initial number n naught of nuclei of plutonium 238 in the power source. So we have to find the initial number n naught. So we have the mass given is here. So out from this mass we have to find the initial number. Now what we need to remember is, so if it is plutonium 238, we must have 238 gram or 0.238 kg of this plutonium written as Pu should have 6.02 into 10 to the power 23 atoms, which is the Avogadro number. This is the Avogadro number, so it should have this much. So that will give me the mass given here is this much. So I must have 0.874 kg of plutonium should have 6.02 into 10 to the power 23 divided this 0.238 into, it should be 0.874. So when I do the calculations, it will give me, so 6.02 exponent 23 into 0.874 divided 0.238 equal to 2.205 and so on. So I just write it as 2.21 into 10 to the power 24. So the initial number of molecules should be equal to 2.21 into 10 to the power 24 molecules. Then I must have then let me just this pen tool from here. Now determine the initial activity of the source. Give a unit with your answer. So initial activity. So this activity is equal to dN by dt initial 0 is equal to lambda n naught. So it must be equal to, now lambda should be equal to 0.693 by 3 by t half, t 0.5 into this n naught is 2.21 into 10 to the power 24, and that's equal to this t half is equal to, as it is given here, t half is given as 87.7 years. So here what you must have is, we have got kg here, so let's change it into SI. This 87.7 will be, so 0.693 by 87.7. when this is multiplied by 365, it will be converted to days, and when it is multiplied by 86400, it is converted to seconds, because 1 year has 365 days, just our average, just normal calculations, and one day will have 24 into 60 into 60, so that is 86400 seconds. So that's why we use this to convert things. Now into 2.21 into 10 to the power 24. So this will be equal to, so let me calculations, so 0.693 divided bracket 87.7 into 365 into 86400 bracket close, into 2.21 into 10 to the power 24. So this gives us, so it is 5.54 something. So it is, I just write here 5.54 into 10 to the power 14 per second. So it will be 5.54 into 10 to the power 14 per second, or this per second can be written as becquerel as well. So it can be written as becquerel as well. So this is the answer for this thing. So now next is use your answer in B2, it means this answer, to determine the initial power output from the source due to the decay of plutonium this much. So now what it says is, so initially the energy given by one, of them is this much, 5.59 into 5.59 mega electron volt. So that's why what I must have is energy of one atom, energy of one atom is equal to 5.59 mega electron volt. So let me confirm it, 5.59. So 5.59, so it should be like this. Yeah, it is given as, yes, 559. So this MeV can be changed to joules as equal to 5.59 into 1.6 into 10 to the power minus 19, sorry, minus 13 actually. If it is mega, it's 13 joules. So energy of one atom is equal to this much. So now, so what we must have is, okay, now it is given that there is a release of initial activity is this much number of atoms per second, and energy of one atom is this much. So the overall energy in 1 second will be equal to, so energy of all atoms in 1 second will be equal to this thing into this thing. So it is 5.54 into 10 to the power 14 into 5.59 into 1.6 into 10 to the power minus 13 per second. So that's equal to joules per second, actually joules per second. So this will be equal to, so 5.54 exponent 10 to the power 14 into 5.59 into 1.6 into 10 to the power minus 13 is equal to, so it is altogether it is 495 joules per second, and that gives us, it is 495 watts. Joule per second is watt. Now the space probe will continue to function until the power output from the plutonium in the source decreases to 65.3% of its initial value. Calculate the time in years for which the space probe will perform. So it will perform till the power decreases to 65.3%. So that means we must have this power is equal to so power is equal to 65.3 percentage of P naught is equal to 0.653 P naught. Also we must have power is equal to power naught e to power minus lambda into time, lambda t. So or I can say 0.653 P naught equal to P naught e to the power minus lambda t. So this P naught and P naught gone. So it should be, so if I take the logs, I will have ln 0.653 will be equal to ln e to the power minus lambda t, which gives us or minus lambda t is equal to ln 0.653. So this gives us this time is equal to ln 0.653 divided by minus lambda, and this lambda is equal to half. This will be equal to ln 0.653 divided, it is minus 0.693 by t 0.5, and that is 87.7 years. So here I do not change it into seconds because the answer is in years. So that's why what I have done here is I have changed this 87.7 years. I have maintained this 87.7 years. So this thing will be equal to, if I do the calculations, so this 87.7 will go up, this will go up, so that's why. So ln 0.653 into 87.7 divided 0.693 equal to minus 53.9 years. So minus minus plus, so it is 53.9 years. So it is 53.9 years. Now, an alternative power source uses energy generated from the reactor of polonium-210. So from plutonium it goes to polonium. This isotope has a half-life of 0.378 years. As you can see, the half-life has decreased, of course, compared to previous value. Previous value half-life is 87.7 years, and here it is 0.378 years. It's very short. The mass of the isotope needed for the same initial power output is 3.37 grams. Suggest one advantage and one disadvantage of using polonium-210 as a source. So first is advantage. So we require less mass. So less mass means that we need less energy to start that stuff. We have to use less mass of things as a raw material. So that's why to lift the probe or to take the probe from Earth to the space or wherever, the energy required will be less. So energy required to launch the probe will be less due to less mass, less overall mass. So now next is disadvantage. So for this we have to know is the half-life is this much. So that means it finishes quickly. Half-life this much means that previously it was 87.7 years and now it is 0.37 years, 378 years. So that's why, since half-life is less, half-life is less, the raw material finishes quickly. Raw material finishes off fast. So we have to replenish them frequently. So that is the main disadvantage of this thing. So this is the solution to this question of these 11 marks.